Hello and welcome back. So what I want to talk to you about today is AM radios. Now back in the day, AM radios were the tip of technology, but lately they have been surpassed by things like FM and DAB radio or even internet stations. The thing is, these alternatives offer far better audio quality and far more diversity. But the thing is, the old radio receivers, once you recondition them, get them up and running, are like industrial pieces of art. I mean, nobody builds things like this anymore. I mean, this comes from a time when having 7 transistors was really a big thing. But the problem is, you take your radio receiver, you repair it, you get it up and running, and you turn it on, and there's not much to do with it. I mean, there's very few AM stations left out there, and there's nothing really interesting to listen to on them. So what I want to do today is build an AM modulator, a circuit that can take an audio signal from an external source like a computer or anything else, send it over a short distance so that your radio receiver can pick it up. The point being that you don't have to make any sort of modifications in your radio. This will be an external circuit. So if you're curious, then keep watching. So let's start off with remembering a few things about AM. Now, from a frequency point of view, there are quite a few AM bands. You've got your long waves, medium waves, and short waves. These are the most commonly used frequency ranges. Now, on the long waves, you don't really have any stations anymore. Medium waves contain a few more commercial stations, and then on the short waves you have both a few commercial stations, but also a lot of amateur radio stations. So you can actually get a radio amateur license, and you can actually transmit on the short waves. But what we're doing today will be very short range, so that's not really applicable. Now, the term AM stands for amplitude modulation. Now, this works by taking a high frequency carrier signal, so this is the signal at which your radio signal is being transmitted, and combining it with an audio frequency signal, so this will be the information that you're trying to transmit, and creating a signal that keeps its base frequency at the frequency of your carrier signal, but the amplitude envelope follows your transmitted signal. Hence the term amplitude modulation. And this is basically the easiest form of modulation you can do, other than pulse modulation, for example. But the drawback is that this sort of signal is very easy to corrupt over long distances, where you can have influences from all sorts of external factors. So other than your useful amplitude modulation coming from your useful signal, you can have all sorts of external parasitics. So to build this thing, you just need 2 basic blocks: your local high frequency oscillator giving you the carrier frequency signal. This can be stabilized with a quartz crystal or not. For a proper transmitter it is stabilized, but for what we're doing that's not really necessary. And your amplitude modulation circuitry, the circuit that combines your high frequency signal with your audio signal. Now, in a proper transmitter, other than these 2 stages, you will have some sort of high power radio frequency amplifier before the antenna, maybe some audio frequency amplification and conditioning, and you can also have all sorts of isolation circuitry or frequency multiplication in between your local oscillator and the amplitude modulator. But the circuit that I want to build today will be the most basic circuit possible, because for a transmission range of 1-2 meters that's what you need, and I will try to build this thing with just 2 transistors. So let's get right into it. Let's look at the 2 blocks one by one. Now, for the oscillator part, I will be using a basic Colpitts type of oscillator, so this is its basic schematic, and the nice thing about this oscillator is that it's pretty bulletproof, so every time I build one of these things it always worked. And these will be the exact components I use. So my supply will be 5 volts. I want to supply my circuit from the USB adapter. Since I want to take the signal from the computer, might as well take the power from there. The only thing to keep in mind with this circuit is that your oscillating frequency will be dictated by your inductor value and the equivalent capacitance of the two capacitors in series. So with this type of oscillator, you can get anywhere from a few tens of kilohertz up until multiple megahertz. So you can build this either in the long waves or the medium waves or even in the short waves. And if we run this thing, we can see that it takes a few milliseconds for the oscillator to start up. But afterwards, if we zoom in, we can see that it will provide quite a clean sine wave. So the signal coming from this doesn't really need any extra filtration to eliminate extra harmonics. Now, for the modulator part, the schematic looks like a typical transistor amplifier, but it has two signal inputs. On the one side we have the radio frequency signal coming into the base of the transistor, and on the other side we have the audio frequency signal coming into the emitter. Or in other words, for the audio frequency signal, the transistor is working in a common base application, whereas for the radio frequency signal, it's working like a common emitter application. To see exactly how this works, I split up the schematic into two pieces. So first, let's look at how this amplifies only the audio frequency signal. So if we look at the audio frequency input and the output, well, they're a bit spaced by a certain amount of voltage, but their amplitude is roughly the same, which is typical for the common base amplifier. But what is important to notice here is that the current going through the collector is changing. So it goes from roughly 3.2 milliamps down to 2.9. And this is important because this will change the impedance in the base. So because the collector current is varying, so is the base current. On a much lower level, but it's different. And this is important because the signal coming from the radio frequency amplifier has a certain output impedance, then you have your series capacitor, and then this meets another impedance here at the transistor amplifier. So to understand how the modulation works, I got these two circuits running, which are basically the same amplifier, only with the radio frequency input, no audio frequency, but I changed this resistor in the emitter to replicate the two currents that go through the transistor. So if we first look at the current we had initially, so we have this nice sine wave, then we look at the current in the two cases, we can see that even though the same input signal is coming and the rest of the circuit is exactly the same, we end up having different currents going through the amplifier. And that is because we have different voltages that appear in the base of the two transistors. So on one side we have this voltage, and on the other side we have a much larger voltage. So when our radio frequency signal sees a high impedance, it requires low current and it can ensure a high voltage amplitude. And when it sees a low impedance requiring higher current, the voltage amplitude will be lower. So all in all, if we now come back to the initial circuit and we look at its output, we see our nice amplitude modulated circuit. Now, it's not a perfect amplitude modulator. You can build that with more complicated circuitry, but this is enough to show the principle. So, not much to do. Let's try to build this thing. This is the final schematic that I came up with. In the first block we have our local oscillator. Then we have our AM modulator that takes this signal and also the audio frequency signal coming from an external source. And finally, I added an extra filter. So as I said, I will be supplying this from the USB from a computer, passing it through a basic filter, and I also added an LED just to show that it's being supplied. So now let's see if it actually works. So I built the circuit on this little board. The only difference from the initial schematic is that I added this trimming capacitor just to fine-tune the oscillator's frequency. So I'll be connecting it to the computer using the USB, but also using a coax cable going into the audio output. So first of all, there's no audio signal. Let's just see what's going on at the oscillator output. So we see almost 800 kilohertz, and while the signal is not a perfect sine wave, it has this flat area here at the bottom, but it's good enough for our needs. Now if we look at the output of the circuit, and reduce the time base a bit, we can see a flat signal amplitude. But now if I turn on the audio signal, 1 kHz sine wave, we see our modulation appearing. So we can see that the signal is modulated with the 1 kHz sine wave. We can see that there's exactly 1 millisecond between two of these peaks, and we can also clearly see how the amplitude is varying. So we have quite a large amplitude and then quite a small amplitude. Likewise, if I change the modulation frequency, say go to 2 kHz, we can see that that happened. So now we're up to 2 kHz and 500 microseconds between the peaks. So the circuit works. Next problem will be how to take the signal from the circuit to the radio. And there's two main ways you can do this. On the one side, most radios, even these portable ones, have an antenna input, so somewhere where you could connect a larger aerial antenna, and you can use the output of our modulator and connect it directly into this input, or you can try to transmit the signal in a wireless way. But considering that we are working at very small frequencies, 1 MHz is a frequency at which the wavelength is very, very long, radiating electromagnetic radiation on a short distance is virtually impossible. So the only other way we can take the signal from our circuit to the radio would be in the form of either electric fields or magnetic fields. And luckily for us, most of the more modern radios, like this one designed in the 60s, have a ferrite rod inside of them. So the main receiving coil is placed on a ferrite rod, and this enhances its sensitivity to magnetic fields. So if we can couple the signal coming from our circuit to this, we will have a pretty good transfer method. And to achieve a proper transfer through magnetic fields, we need to build an inductor. And there's two ways we could try to do that. On one side, we could go for the solenoid shape, so single layer and multi-turn, and on the other hand, we could go for the spiderweb shape, single turn and multi-layer. The main difference between the two, if you get them to the same diameter that is the way in which the radiation spreads out from the inductor. For the solenoid shape, you have a very directional field that comes back close to the inductor, and although this should be able to achieve the highest distance, if the inductor and the radio are not perfectly aligned, so if there's any sort of misalignment, then the two will couple very poorly. On the other hand, with the spiderweb shape, the field is far more spread out, so you don't have a very linear field, but rather it spreads out all over the place. And you have this sort of inductor commonly used with things like wireless charging or induction heating. And that is because you don't want to have a single position in space where you can charge your phone. You want it to work wherever you put the phone onto the coil. So for this application, since we don't want to have a very, very precise alignment between our receiver and the coil, we can go with this sort of inductor shape. So everything's hooked up. I got my transmitting coil, I got my AM radio that's making a lot of noise. So now let's play some music. So we can see that there is a certain amount of orientation related amplitude modification. So if the radio is properly aligned with the coil, it works better. If not, it doesn't. But even if I take it to about a meter from the inductor, there is still some sort of sound going through it. Now, it's not the cleanest sound, and there's two reasons for that. On the one side, the amplitude modulator isn't perfect, so you can make far better amplitude modulator schematics than this thing. And on the other hand, in most AM radios, because of the way in which the frequency bands are allocated, you can get a maximum of 5 kHz of bandwidth. So you can definitely not hear the high frequency sounds that are around in most songs. So that's why AM radios sound a bit poorer in sound quality. But it works. It's not perfect, but it's an interesting way to get your old AM radios to play something a little bit more modern. There is of course a lot of things that can be done with the circuit to make it work a bit better, maybe add an extra radio frequency amplifier at the end to increase the range. But all in all, it's a nice circuit. So, hope you got some useful information after this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos. And see you next time. Bye bye.